This is day 3 of static electricity and electric fields. That's chapter 16 of our textbook. Alright, so let's start with a warm-up. In our warm-up, you see two balloons there attached to strings, but notice that the balloons are far away from each other. So what keeps them separated? That's the question for a warm-up. The answer is likely both of these balloons are filled with charges, negative charges, electrons, and charges they repel. Now, how much force is keeping them away from each other? And how much of that force creates an electric field? That's what we'll be looking at today. So the objective of today's lesson, students will be able to use pertinent formulas to solve for the strength of an electric field. Alright, so right here I wanted to show you guys this diagram. In this picture right here they have two plates and they have a charge, so they develop an electric field. Now an electric field, you can't really see it, so what they do is they put metal fillings all around, and the metal fillings will line up matching that electric field. So that's the lines you see is actually metal fillings, which allow you to see the field. So it says the area around an object where a magnetic force exists is defined as the electric field. Alright, so that's why all the metal fillings are reacting to the two bars right here. Now the forces exerted by an electric field can do work or transfer energy from one field to another. If you ever held two charges, two magnets of opposite charge together, and you bring them together, they'll attract each other. But if you flip one of them, and now they have the same charge, they're going to go ahead and repel each other. So you'll need to do a lot of work to bring them together, or it actually, one magnet could push away the other one. That's another definition of doing work. Okay, so the strength of an electric field can be measured by the equation E equals F on the charge divided by the actual charge. Alright, what is E? E is the electric field strength, that is in newtons per coulombs. The F is the force on the charge, which is in newtons, and Q is the test charge, the positive test charge measured in coulombs. Alright, so now this formula can be used to derive this other formula right here, where E is electric field strength and newtons per coulombs. K is Coulomb's constant, Q is the charge produced by the field, and R is the distance between the charge and the field. Alright, so how do we go from this formula to that formula? I wanted to go ahead and take a moment to show that. So starting with this first formula, what you would do is move the Q over to this side, isolating the F. So now we have the F isolated. We're going to go back to this previous formula we've used before and substitute the Q and the E where the F is at, since they equal F, so you see that right there. What's next for us? Well, we're going to go ahead and now isolate the E by dividing by the Q. So that's gone. And you'll notice that also on this side, one of the Q's is gone. So what does that leave behind? That gives us E equals Kc times Q over R squared, which is the formula we have right there. Alright, so that's how that formula is derived, and we're going to be using it to figure out the field strength, the electric field strength for the problems we'll be looking at today. Just to give you guys an idea of some values. Approximate values of typical electric fields. If you're near a charged rubber rod, alright, so that will go ahead and give you a 1000 newtons per coulomb field. If you have near a television, television will also give you a charge of 1 times 10 to the 5. To create a spark, you need 3 times 10 to the 6, and an electron's orbit on a hydrogen atom has an electric field strength of 5 times 10 to the 11. Alright, so those is just to give you an idea of what kind of answers we're going to get. So we're going to get some pretty big answers out of these problems. Alright, so let's start with sample problem D out of page 574 of your textbook. In this one, they ask you as the following. It says, a charge Q1 has a charge of positive 7 microcoulombs, which is 7 times 10 to the negative 6 coulombs, is at the origin. So there we go, right there. And a charge of Q2 has negative 5 microcoulombs, which is the same as negative 5 times 10 to the negative 6 coulombs, and is on the x-axis, 0.3 meters away. So here we go on the x-axis, and there's the distance between them. Alright, find the electric field strength on a point P on the top, which is on the y-axis at 0.4. So notice y-axis I go up by 0.4, so there you have it. And that's all the information that's given to us. Now, they did say this is on the x-axis and y-axis, so we can conclude that this is a right triangle. Now, since I know it's a right triangle, I need to figure out this length. I'm going to need it, so it's going to be a squared plus b squared equals c squared. So we end up with that being a 0.5. So that's the value of this hypotenuse of our triangle. Alright, so now that we got all that information, we need to go ahead and figure out the field strength for Q on P, Q1 on P, and Q2 on P as well. Alright, so let's get to work on that problem. Our formula is the electric field strength is Coulomb's constant times the charge divided by the radius squared. Alright, so let's get to work. So electric field for the first one is going to be Coulomb's constant, which is 9 times 10 to the 9 newtons times meter squared over Coulomb squared. The charge, 7 times 10 to the negative 6 coulombs, divided by the distance squared. Distance between Q1 and P is 0.4 meters. And we're going to go ahead and square that. Alright, so our answer, 9 times 10 to the 9 times 7 times 10 to the negative 6 divided by 0.4 squared gives us 393,750 newtons per coulomb. Alright, that is our first value for E between Q1 and our point charge. For Q2, we're going to do much the same. So it's going to be Coulomb's constant, 9 times 10 to the 9, multiply times the charge, divided by the distance, which is 0.5. That gives us a value of 180,000. Alright, now, our next step is to figure out how is that going to affect the point charge up here. The point charge will have a positive value. So the fact that these two are positive between Q1 and the point charge means that our P is going to be repelled, so it's going to go in that direction. By how much? By 393,700 newtons per coulomb. On the other hand though, Q2 is negative. Negative, if our point charge is positive and that is negative, what's it going to do? Opposites they attract, so it's going to be pulled towards Q2. How much? It's going to be pulled by 180,000 newtons per coulomb. Alright, so that's the field that it's experiencing, that P. It's going to be pushing that way, but pull this way. Alright, so what ends up happening here? Well, we're going to need this angle right here to figure it out. Then we're going to do a vector diagram to solve for that. And after that, we're going to go ahead and solve for the net force acting on it, or the net electric field acting on it. Alright, so let's start with this. How do you solve for that angle? Well, we have a right triangle, and we have pretty much every side, so we can use either sine, cosine, tangent, does not matter. Let's just use with the most common one, which is sine. Sine is opposite over adjacent. So this angle right here, I'm going to label it theta. So theta is, pardon me, sine of theta. It's equal to opposite, 0.3, over hypotenuse, 0.5. To get the actual theta, I'm going to have to do inverse sine of 0.3 over 0.5. Alright, so answer for that, inverse sine gives me 36.8. I'm just going to round it off to 37 degrees. So that's the angle at that spot. Great. Now we're going to go ahead and do our vector diagram. And I'm going to start with this arrow going up and then the one to the side. So All right, first one, the arrow pointing up, 393,750. All right, so I'm going to go ahead and go with, let's see, how big should I make that? 39 inches would be much too big. That's too big for the board. All right, so let's see. Let's go cut it down to a third, so 3 inches would be much too small. You won't be able to see that. So let's just go with something in between. Let's just get this number and double it. So I'm going to say alright, so that represents 393,750 newtons per coulomb. Alright, so that is this first one going up. Now the next one, at what angle will we put it at? We're going to put it at 37 degrees. So this next one's going to be at 37 degrees. And when you're drawing a vector diagram, where one arrow ends, that's where the other one begins. So this arrow pointing down, the tail of the arrow will be here and the arrowhead will be down here. Alright, so for this one's going to be 180. So that's going to be about that big in this diagram, give or take. That's 180,000 newtons per coulomb. Alright, so there we have it. So what are we really solving for? We're solving for the resultant, which will be right here. That's what we're solving for. Alright, so that black arrow is our resultant, and that is our goal, to go ahead and solve for that. Alright, so how can we do this? You've seen this before. We have side, angle, side. So therefore we can get the resultant using law of cosines. And that's the route we're going to go ahead and get. The resultant is a squared plus b squared minus 2a times b times cosine of the angle in between them, which is 37, so that's a theta. Alright, so the resultant is going to be a 393,750 squared plus b, which is 180,000 squared, minus 2, which is 393,700 times b, 180,000 times cosine of 37. Alright, so that will be our setup. First I'm going to go ahead and square both of these and then add them up. So let's see, 393,750 squared plus 180,000 squared equals 1.87 times 10 to the 11. On this side, let's see what we get. Cosine of 37 times 180,000 times 393,700 times 2, it's equal to 1.13 times 10 to the 11 as well. So now we're going to go ahead and subtract 1.87 times 10 to the 11 minus our answer gives us 7.37 times 10 to the 10. Finally, to get the r, we need to get rid of that square, so we're going to square root. And our answer is 271,649 newtons per coulomb. Alright, so that is the value of this side of the triangle. And that is our answer. I'm sure if you look at it in the book, it's going to be rounded off. Let's see, they give us two significant digits in all of these. So round it off to 200 to two significant digits, 270,000. Alright, so that's more likely, if you look it up in the back of the book, that's what you will see. Alright, so that takes care of sample problem D out of page 574. Up next is practice problem number 1 out of page 575. They ask you, as a charge Q1 is 5 microcoulombs here. I already put it in coulombs here, 5 times 10 to the negative 6. It's at the origin. And the second charge Q2 is negative 3 microcoulombs, which I put already in coulombs, 3 times 10 to the negative 6. It's on the x-axis at 0.8 meters away, so there's 0.8 meters. Find the electric field strength at the point, which is 0.5 meters above the origin. Alright, so there we go. So they give us all these numbers. I have the 0.94 here, which I got. We are going to use Pythagorean theorem to solve for this one. A squared plus b squared equals c squared. That's how we got the 0.94. Alright, so that's all the information we need out of this problem. Now we need to figure out what is the electric field strength for Q1 on P and Q2 on P as well. So let's get to work on that section. So for this one, for Q, is going to be coulombs constant, 9 times 10 to the 9. Multiply times the charge. For Q1 it is 5 times 10 to the negative 6. And all of it divided by the distance between them, which is 0.5 meters squared. So electric field strength has a value of 9 times 10 to the negative 9 times 5 times 10 to the negative 6 divided by 0.5 squared equals 180,000. Alright, the next one is going to be for the electric field strength created by the second charge. Alright, for this one, we still use the constant, Coulomb's constant. The charge, 3 times 10 to the negative 6 coulombs, divided by the distance between them, which is 0.94, squared 9 times 10 to the 9 times 3 times 10 to the negative 6, divided by 0.94 squared, gives me 30,557 newtons per coulomb. Alright, now which directions are these guys pulling the charge? Let's talk about that. The first one is positive, so that repels our positive charge away. The next one is negative, so that attracts our positive charge towards. So it's going to go in that direction. Again, very important for us is to go ahead and pick up what is that angle then between them. We're going to use it to draw our vector diagram. Alright, so the angle, in this case we can use sine of 0.8 over 0.94. So it's going to be sine of theta. It's equal to 0.8 over 0.94. To get the theta by itself is the inverse sine of 0.8 over 0.94. So you plug that into the calculator. You get 58.3 degrees. We'll just round it off to 58 degrees. So that is our angle at that spot. Now we can go ahead and draw our vector diagrams. First I'm going to draw the arrow pointing straight up. That one has a value of 180. Alright, so we're going to go with, let's go with 18 inches. So there's a value 180,000. Alright, and the other one's at 58 degrees. It's going to have a value of 30,000. So we're going to go with that, just 3 inches. So the angle is 58, so I'm going to try to honor that angle, and it is just 3 inches because it's only 30,000. 30,557 newtons per coulomb. That is that little arrow right there. And the question that is asked of you is, can you figure out what is the resultant from these two vectors? So it is from this point to that point. What is the length of that black arrow right there? Now that we have the value for E1 and E2, we can go ahead and put it together in this vector diagram. So our first vector, since it's going straight up, we're going to go ahead and have our vector going straight up as well. 180,000 is its value. Next, at an angle of 58 degrees pointing downwards, so there we go, downwards is our second created by the Q2, which is 30,000. So notice 30,000 is much smaller than 180, so you see a smaller arrow. And the question is, can you figure out what is this black arrow right here? That's the resultant between our two vectors. Alright, so now we do have side angle side. Side angle side means that we can use law of cosines to solve this problem. Law of cosines is r squared is equal to a squared plus b squared minus 2a times b times cosine of theta, theta in this case being 58. Alright, so next, what is A? A is going to be 180,000. I'm going to square that, plus B, which is 30,557 squared, minus, I don't have space here, so I'm just going to continue on the bottom, minus 2 times A, which is 180,000, multiplied times B, 30,557, times the cosine of our angle, which is 58 degrees. Alright, so that's what we have. Now we need to go ahead and plug into our calculator the values. And so we're going to go ahead and multiply first this part, square, square, and add. So 180,000 squared plus 30,557 squared. That gives me 3.33 times 10. That's the value for that. Minus on this side. Now let's take care of this side. Cosine of 58 multiplied times 30,557 times 180,000 times 2. It gives me 5 billion. It's too bad it did not give it to me in scientific notation. I would have been nicer. 5,829,387,465. Next, I subtract both of these values. And that gives me 2.74 times 10 to the 10. Next, R, I want to go ahead and want it without the square, so we're going to square root to get rid of the square. So our answer is 165,742 N over C. That is our value for the length of that arrow. Alright, so that is practice problem number 1 on page 575. Up next is practice problem number 2 out of page 575. In this problem they ask you guys, a proton and an electron in a hydrogen atom are separated on the average by 5.3 times 10 to the negative 11 meters. So here we have a proton, the electron, and that is the distance in between them. Alright, what is the magnitude and direction of the electron field set up by the proton at the position of the electron? Alright, so for this one, let's see, the charge of the proton is given to us right here. They want to know what is the electric field strength. So it's going to be Coulomb's constant, which is 9 times 10 to the 9 newtons times meters per second, newtons per coulomb squared. Multiply times the charge of the proton, since they asked for the proton, and that would be 1.6 times 10 to the negative 19 coulombs, divided by the distance between them, which is 5.3 times 10 to the negative 11 meters, and that is squared. Alright, we plug all of this into our calculator, and that will give us our electric field strength set up by the proton. So it's 9 times 10 to the 9 multiplied times 1.6 times 10 to the negative 19 divided by 5.3 times 10 to the negative 11 squared. And that gives us a value of 5.13 times 10 to the 11 newtons per coulomb. Alright, so that would be the answer to this question. Up next is practice problem number 3 at page 575. In this problem they say an electric field of 2 times 10 to the 4 newtons per coulomb is directed along the positive x-axis. What is the electric force on an electron in this field? That's part A. And part B, they say, what is the electric force on a proton in this field? Now, let's write down some values that we do know. They give us the electric field of 2 times 10 to the 4 newtons per coulomb. Next, we know that the charge of a proton and electron is 1.6 times 10 to the negative 19 coulombs. It's the same value for both, except one is negative, one's positive. And what they're asking here is for what is the force. Alright, so we're going to use this formula that was given earlier, and we're going to move the Q over here to solve for the force. So we end up with this formula. Force is equal to the charge multiplied times the electric field. Alright, so we're going to plug them in. So for the electron, you're going to see the charge of the electron, which is negative, times the electric field gives us a negative 3.2 times 10 to the 15. For the proton, so here the piece for proton, it's a positive value, but notice how it's the same number, so we end up with the same number, but positive. So both the proton and the electron, because they have the same charge, gives us the same force, except that one is negative, pointing in the negative x direction, versus the proton is positive, pointing in the positive x direction. So the direction is the only difference between both of these. So these are their answers, and that is practice problem number 3 out of page 575.